This is question 1 from page 10 of the structures notes, first of the 6 tutorial questions. And in these questions, we're asked to, first of all, represent the scenario we've been given, the free body diagram, and then to use what we know about static equilibrium in order to find the reaction forces RA and RB. So we'll begin by drawing a simple free body diagram that retains all of the essential information. So free body diagrams allow us to simplify the structure of the bridge to a simple line. So this line represents the bridge. And the important things to include in a free body diagram are all of the forces, the size of any forces that we know, and the distances between them. So I can see in our bridge here, we have a force labelled RA at the left, a force labelled RB at the right. We've got two downward forces, and we can choose to draw these as arrows acting downwards from the line or down onto the line. The direction is the important part. So the way I usually draw things is acting down the way. So we have one force, which is going to be in the middle of the bridge of 500 kilonewtons. And we've got a force that's 25 meters from the left of 15 kilonewtons. And we can include all these distances here. So there's a 25 meter distance from the left-hand side to the 15 kilonewton force, a further 25 meters between the 15 and 500 kilonewton forces, and the distance from the 500 kilonewton force representing the weight of the bridge to the right-hand side of 50 meters. And what we've taken here, all the essential information from the question. We now need to find out what RA and RB are equal to. Well, we can see with a bit of simple addition that there's a total downwards force of 500 plus 15, so 515 kilonewtons total, which means that RA and RB must add up to give us that number, but we don't know what the division between those two is. It's not going to be the same. The forces are not evenly distributed across the bridge. So what we need to look at first is the equilibrium of moments affecting the bridge. So the formula we're going to need to use is this one here. So sigma, meaning the sum of all of the CWM clockwise moments, is going to be equal to the sum of all of the anti-clockwise moments. And this is true at any point along the bridge. We can pick any point in the bridge, and if we add up all the clockwise moments and we add up all the anti-clockwise moments, they'll be equal to each other. But we're not interested in any point in the bridge. We want to pick one point in particular. The point we need to pick is one which has a force at that point where we don't know the value, meaning there's two candidates. We can either work out all our moments from point A, or we can work out all our moments from point B. Either choice will end up giving us the right answer. So there's no particular one we have to pick for this. We just have to pick one of them. And because it's what we've been doing in class, I'm just going to start at the left-hand side. So every moment that I'm now about to calculate, I'm going to mark this little point in red in the left-hand side of our free body diagram. I'm going to be taking moments from this point. So every force that I now multiply by distance, the distance from where that force meets the bridge to the red dot at point A. So if we remember that a moment is the force times the distance away from the point at which we're thinking about rotation. So let's look at our bridge. We don't need to think about the force RA because it won't have a moment at itself, at zero distance from itself. There are three forces we need to look at: the 15 kilonewton force, the 500 kilonewton force, and RB. And each of these is going to provide a moment relative to point A, and the moments will all be clockwise or anti-clockwise. If we look from point A, looking at the bridge spanning to the right, we can see that two of the forces are pushing down the way and one of the forces is pushing up the way. If the bridge structure were free to rotate around that point, those two forces of 15 and 500 kilonewtons would be clockwise. So you can see that these would act to turn the bridge in a clockwise direction if there was free rotation around point A, because they're pushing down the way. And the force at RB, that's going to be anti-clockwise because it's pushing it up the way. If that line arcing the length of the bridge could rotate freely around that red dot, pushing the line up the way to the right would be an anti-clockwise turning effect. So when we come to add up our moments, we're going to have two moments to add up on the left, two clockwise moments, and one moment to add up on the right. So let's do that. So remember, to find each moment, we take each force and we multiply it by the distance from the point. In this case, our point is a red dot. The first clockwise moment is caused by our 15 kilonewton force, multiplied by the distance of that force from A. And the distance that we can see here is 25 meters. So we multiply that 15 by 25. And we know we've got a second clockwise moment because the 500 kilonewton force will also provide a clockwise moment. So we add on 500 and we multiply this by the distance from point A. And if we just look here, the distance from A to where the 500 is the two lots of 25. So it's 50 meters, not 25, it's 50 meters there, times 50. Looking at our anti-clockwise moments, well, we've identified that there's one force that will give us an anti-clockwise moment, and that is the force RB. And that will also be multiplied by the distance from A to B. And that distance is the full length of our beam, 25 plus 25 plus 50, which is, of course, 100. So we start to tidy all of this up and we do some calculations in order to get the correct values here. So first of all, 15 times 25 gives us 375, and 500 times 50 gives us 25,000. On the right hand side, when we have an unknown letter, which we call a variable multiplied by a number, we just write the number, then that unknown, so it's 100 times RB. On the left hand side, we can add these two things together, which gives us 25,375, 25,375 is equal to 100 RB. And then to find RB by itself, well, one thing we're allowed to do in math is we can swap things over and divide, but we'll divide first. We want to get RB by itself, so we can divide both sides by 100. So we're going to have 25,375 divided by 100. And we've got 100 RB divided by 100, but hopefully we can see 100 RB divided by 100 is just RB. And we can write this the other way around now. RB is equal to, well, 25,375 is equal to 253.75. And remember our units for force. We haven't had to do any changes here, so they're exactly as they were to begin with. They are in kilonewtons, so we can write that down. So we found RB. Now we just need to go back to the start and remember what we said. We said the total downward force was going to be equal to the total upward force. So this is our formula here. The sum of all the upward forces is equal to the sum of all the downward forces because we have equilibrium. Well, our upward forces are RA and RB, and our downward forces are 15 and 500. Now we have worked out RB, so we can substitute RB for the correct value. RA we still don't know. RB is 253.75, and 15 plus 500 is 515. So RA is going to be the total downward force, 515, minus the value we found for RB, which is 253.75. This becomes just a quick entry into our calculator, giving us a value of 261.25 kilonewtons. And that's our final answer. We have drawn a free body diagram representing the problem. We have used the equilibrium equation for moments in order to find one of our reactive forces, and then we've used our equilibrium equation for vertical forces to find the other one, giving us the correct answer to the problem.